Alright, so in the last video, we found the general solution, what y equals, but it still has these random constants in them, C1 and C2. So we need to plug in our initial conditions. So this is just a really long question, so we couldn't fit it into one video. There's no problem with that, we'll just finish it here. And I guess you can just skip this video because it's just, it's nothing new being practiced, it's just solving for initial conditions, but I figured I'd just finish it anyways. So we have y equals c1 e to the negative 2x plus c2 x e to the negative 2x plus 5 halves x squared e to the negative 2x. And we have our two initial conditions right here. So one thing I realize is, oh no, we need to find a derivative to use this second initial condition. And we have two power rules right here. So I don't know, you just live through the pain. Just keep going. So c1 e to the negative 2x times negative 2, because we have that chain rule, plus, well, we have a power rule right here, two functions of x. So we'll find the derivative of the first, which is just a constant, times e to the negative 2x, just times the second as is, plus the derivative of the second, so e to the negative 2x, times negative 2, times the second, c2x. And that is done. So now we go to our second one, where we have two functions of x. So we have 2x times 5 halves, so just 5 times x times e to the negative 2x plus e to the negative 2x times negative 2 times 5 halves x squared. Now let me just double check that this is all correct, because I do not want to make a mistake here and have to start over. So I think we're doing pretty good so far. Yeah. Wait, what's this right here? Yeah, we're good. So let's simplify this out. We get y prime equals, I wish I knew how to edit so I could just like cut out those parts, but too bad. Just watch Khan Academy. C2e to the negative 2x minus 2c2x e to the negative 2x plus 5x e to the negative 2x minus 5x squared e to the negative 2x. So this is our derivative of the final equation. And now we're getting pretty close. We just need to plug in our initial conditions. Y of 0 equals 1, y prime of 0 equals negative 1. So, let's do that. Let's get rid of these little scoops right here. And we'll start with the initial condition for just regular y. So, y of 0 equals 1. So we get 1 equals c1 e to the 0 plus c2 times 0 times e to the 0 plus 5 halves times 0 squared times e to the 0. So this just turns out to be 1 equals C1, because C1 times 1, plus, well, 0, plus 0. So we just get C1 equals 1. Not too bad. Well, now let's try y prime of 0 equals negative 1. That's our other initial condition. So we get negative 1 equals negative 2 C1 e to the negative 2 times 0 plus C2 times e to the negative 2 times 0 minus 2C2 times 0 times e to the negative 2 times 0 plus 5 times 0 times e to the negative 2 times 0 minus 5 times 0 squared times e to the negative 2 times 0. So we get negative 1 equals, well, this is just 1, negative 2C1 plus C2, because that is just 1, and then plus 0, and plus 0, and plus 0. So, we get, well, C1 is 1, so we can plug in just 1 here, and we get, well, we get C2. We add 2 to both sides, we get C2 equals 1. And they both equal 1. So that actually works out pretty well. And let's just finally write out our answer, where C1 equals 1, C2 equals 1. So we get y equals, we can just plug in C1 and C2 here, so we get y equals e to the negative 2x plus x e to the negative 2x plus 5 halves x squared e to the negative 2x. And that is our final specific solution to this differential equation. And the beauty of this is this times 4 plus its derivative times 4 plus its second derivative equals exactly 5 times e to the negative 2x. And I think this is the only equation that will satisfy that. It's just cool how so many years of math can lead to just something so complex. And there's actually applications for this in like thermodynamics and like spring oscillations and everything. But you'll probably never need to use this. But I think that kind of finishes up our like second order differential equations unit. I think in the next few videos, it's our last unit. It's called Laplace transforms, where we have this cool little L right here. And what's cool about Laplace transforms is any function, like if it has a e or something, or sine waves in it, like radicals, Laplace found out that any function can actually be rewritten as a polynomial function. It just gets exponentially like harder and harder to like find. Just gets longer and longer. But you can, I guess, just define this as a polynomial function like x squared plus 4x. And then there's Fourier series, which does the same thing, but with sine waves. And that is applicable to radio transmissions and everything. But we're just going to be focused on Laplace transforms in the next unit.